Today, I want to start and probably finish our review on for Exam 8 on Chapter 16, acids and bases. Let's see. And I'm working from the review document, and I've highlighted some as usual. I want to be sure and get to. And we're going to start with number 3. Which of the following is the strongest conjugate acid? During the lecture, I introduced the topic of acids and bases. Say you have an acid and it's reacting, of course, with water. And the proton is transferred to the water, so that makes this the acid of Bronsted-Lowry acid. This makes water the base. And what we end up with is this conjugate base. And the hydronium then would be the conjugate acid. Okay? If we're looking for the strength of a conjugate acid, we go to the base from which it was drawn, from which it was created. Right? If we want the strongest acid, we go to the base. If this is strong, then the base has to be weak. We want the weakest base. All right? That may be, I think we can make it even simpler than that. Since all of our choices here are acids, hypochlorous acid is the first one, hydrocyanic acid the next one, hydrofluoric acid is the next one. Ammonium ion is an acid. Remember how that's formed when we have ammonia and water. We get ammonium and OH. Okay. So this is a conjugate acid. So we're looking at acids here. We want to find the one that is the strongest conjugate acid. Let me see. If we look just at ammonia, ammonia is a relatively weak base, which would, by comparison, make this a strong acid. But we also have various acids there that we need to consider. And when we look at what makes a strong acid, I think that's a better approach. What is it that makes a strong acid? Right? When you have a proton bound to some other group, the strength of the acid depends on the polarity of the bond So that means if the bond is more polar toward this group, then that means electrons are withdrawn toward that, and it weakens the bond. So that makes the hydrogen more ionizable. So what causes the bond to be weakened? Well, we look at the electronegativity. If there's a single element here, the electronegativity will be a clue, right? So let's see, A, B, C, and D, and E. So the first one is HOCl, HCN, HF, and NH plus. And then we're saying all of them are equal. Well, we know they're not all equal. The electronegativity of fluorine is very high. Right? Electronegativity is very high, which makes that a good candidate for a strong acid. The electronegativity of carbon and nitrogen, both of them will be less than that for fluorine. So this is going to be less than that one, right? When we're ordering strength, this one is less than HF. How about this one? Well, this one has an oxygen in it, so this is more electronegative than either of these. So this one is going to be more acidic than this one, but less acidic than that one, because fluorine is the most electronegative element in the periodic table. Plus, it's small. It concentrates that electronegativity and the charge into a very small volume, which gives it an extra partial charge. Okay, so what I'm saying is, so far, we've got this as our best candidate. Now we have to say, how does it compare to this one? Well, that's a good question. I think probably what we're looking at here is when we've got this ion, if we compare nitrogen to fluorine, nitrogen is not as electronegative. It's on the order of this one up here. So as a best guess, I would say hydrofluoric acid is probably the strongest acid in that bunch. Now you'd have to actually see the numbers, see the equilibrium constants to verify that. But I think we're pretty safe in saying that HF is the strongest acid in that group. Okay, 4. Calculate the hydrogen ion concentration in molarity in a solution that has a pH of 8.82. This is very simple. We just need to know what is that equal to. That's equal to the negative log of the hydrogen ion concentration. Right? So we know how to handle logarithms. This is base 10. So we take the negative over here to this 8.82. And then we say, what power of 10 is equal to that? Well, this is the power of 10 that's equal to that concentration. So it's 10 to that power equals hydrogen ion concentration. Right? And if we do our calculations correctly, we should get 1.5 times 10 to the minus 9th molar. Now, let's see, we have the right number of significant figures. We have 2 decimal points here, 2 significant figures there. We're good. All right, number 5. A solution is prepared by dissolving 111.9 grams of HCl gas. So the mass is equal to that. Grams of HCl gas. In how much? in enough water to make 160 liters. The volume equals, yes, 160.0 liters. All right. And what's the pH? Well, we've got to calculate the hydrogen ion concentration somehow. Can we do it with this information? Not directly, because that's not moles. What we need is moles of hydrogen chloride. So in order to do that, we need to get rid of grams and leave us with moles. And that's molar mass. So the molar mass of HCl is 35.45 for the chlorine and 1.01 for the hydrogen. 6463. So that's the number that we divide into 111.9. Let's see, 111.9, 36.46 divide, and I get 3.069117 moles of HCl. Okay. Now, how do we get the hydrogen ions out of that? Well, this is a strong acid. So everything, all of this is going to be converted 1 to 1. For every mole of this compound, you get 1 mole of hydrogen ions. So if we calculate the molarity of H plus, then we have 3.069117. And notice I'm keeping a lot of decimal points here. That's so that I can avoid rounding errors. All right. We'll bring in 4 significant figures at the end. Moles and liters. We're good there. All right, so I'm going to divide 160 into that. And that's 1.1, 1.9. I can do better than that. 1.918 times 10 to the minus 2 molar hydrogen ion concentration. So all we need to do is take the negative log of that value. Right? Negative log of 9.182 times 10 to the minus 2. And let's take the log, change the sign. And my calculator tells me 1.717107. I can have, how many decimal points can I have in that pH? Well, we got 4 significant figures here. I can have 4 decimal points. So we draw the line there. Right? 1.7171. Or the closest one that you have available there is 1.72. Okay, number 6. A solution has hydroxyl ion concentration of 5 times 10 to the minus 4. (5.0) minus 4 molar. Question is pH. What's the pH? Well, we have 2 options. We can do it the long, hard way, and we can use our formula. Right? Find out what this is, then take that. Or we can use this formula. pKw equals 14, equals 14, which is equal to pH plus pOH. I think that would be easier. So we just convert this into POH. Okay. All right. And pin, share. Okay, we're back. So this calculates POH. So I say 5 and to the power of -4 and take the log, change the sign. So this is 4.4.00 POH. That means pH equals 14 minus 4.00, which is equal to 10.00 pH. Let me try that again. 5 minus 4 enter log. Oh, that's wrong. This should be 3.30 POH. Calculation error. 3.30. And this one has infinite significant figures. Right? It's an exact number. So subtract that from, let's see, change the sign. Here we go. And then 14. This is 10.7. 10.7 pH. 10.7. Oh, yeah. But this is a subtract rule, right? When you have this one, 3.30, then we go there, and that's 10.70. Okay, so that's the correct answer, 10.70 pH. Number 7. As water is heated, its hydrogen ion concentration increases. This means what? Well, we're talking about pure water here. And so if we take pure water, right, and we increase the temperature, what that actually does is it says this one plus this one, L, L. Now it still transfers a proton over here, which makes OH minus and H3O plus, right? So if we increase the temperature, we should shift the equilibrium this direction, right? We're providing more energy to release protons. So the concentrations here increase. Okay? So what does that do to the balance? Right? We have an increased concentration of hydroxyl, but we have exactly the same increase in hydroniums or hydrogen ions. So this relationship that still stands exactly the same. Although these are larger values, they're still equal. So hydrogen ion increases. It's still neutral because the hydrogen ions and the hydroxyl ions are equal in concentration, right? That's the definition of neutrality. And hydroxyls also increase. So E is the correct answer. Both A and D are correct. Okay, number 8. Number 8. Identify the Bronsted acids and bases in the following equation. Okay, A and B. So if we have HSO3 minus, which is the hydrosulfite polyatomic ion. And then we're going to have cyanide ion. And that's going to lead to HCN plus the sulfite ion. Okay? So by definition, which one of these loses an electron? This one, because we have this to show for it over there. So this proton goes like that. That makes this the acid and this the base. And the conjugate acid now is this one, and the conjugate base is that one. So ABAB would be the correct answer. Number 9. Which of the following is a conjugate acid-base pair? I remember during lecture, I cautioned you about identifying 2 items in a proposed pair. One is that you only lose 1 proton at a time. And what you have left over then is that. Right? Or if you have this, lose 1 proton, you have that. Okay? So, which ones qualify? Well, the first one shows us that we have hydrophosphate to phosphate, loses 1 proton. A is a good answer. If we look at the rest of them, we see that the well, B, D, and E don't work. The reason, well, actually, all of them don't work. Well, B doesn't work because this part of the molecule right here, is not correct. But C, D, and E don't work because those acids don't exist. NH4 doesn't exist. You can't make that compound. H2F doesn't exist. H2CN does not exist. Plus, H2CN says that you're losing 2 protons to get to CN minus. And that doesn't work. I mean, the charge balance is wrong, for one thing, and you're losing 2 protons is the other problem. For H2F to HF minus, HF is neutral. It never has a minus charge. You can only connect one hydrogen with one fluorine. It won't exceed that. And you can only connect one hydrogen with ammonia to make NH4 plus. NH4 plus is a valid acid. But if that's the acid, then the base would have to be NH3. All right, so the only one that works in that group is A. All right. Number 10. Choose the case that is not a Bronsted conjugate acid-base pair. All right, so this is like number 9, only now we got to pick the one that's wrong. All right, the first one, A, B, C, D, and E. What do we got with A? Well, we've got one proton from HCN being lost and producing CN minus. That's a good one, right? So this is not an answer, right? That's a valid acid-base pair. We're looking for the one that's not. CH3 NH3 plus. Notice that we're losing a proton there, but it's coming from the nitrogen side of the molecule, and it's taking that plus with it. So B is correct also. That's a correct acid-base pair, so that doesn't answer our question. How about HCO2H? HCO2H and HCOH. HCOH. Right. What would we have to do? Well, we'd have to lose. Oh, that's easy. You got 2 oxygens here and only 1 there. Right? That's a good one for the answer. H3BO3 and H2BO3 minus. That works. Loses 1 proton. Left you with a negative charged conjugate base. HClO2, lose 1 hydrogen. Leaves its electron behind, ClO2 minus. That's a good one too. All right, so neither one of these work. C is the only one that is not a valid conjugate acid-base pair. All right, number 11. Calculate the hydrogen ion concentration in a solution that has a pH of 9.16. We did one like this before, I think. If pH is 9.16, then the hydrogen ion concentration would be 10 to the minus 9.16. Right? And that should be 6.9 times 10 to the minus 10. Molar. Okay. How about 15? Okay, calculate the pH of an acid solution containing 0.044 molar HNO3. All right. First of all, we know the concentration of HNO3. The question is, what's the concentration of hydrogen ions? Before we can calculate pH, we have to know that. Well, this is a strong acid, right? So that concentration is the same as the hydrogen ion concentration. So all we have to do now is say the negative log of this value. And that should give us 1.36. Okay. All right. 3 decimal places. Let's see. 2 decimal places, 2 significant figures. That's good. How about number 16? What's the pH of 4.9 molar HClO4 solution? 4.9 molar HClO4 solution. Perchloric acid is a very, very strong acid, and it will dissociate into 4.9 molar hydrogen ion concentration. So if we take the negative log of that value, right, take the negative log of that, pH then, I suspect, is going to be a negative number. 4.9, take the log of that and change the sign. Yep, this is negative 0.69 pH. I think the point of that problem is just to reinforce the fact that this is a simple calculation, so your answers can come out positive or negative. Whether that's a practical expression is another issue. All right, number 17. What's the pH of 0.25 molar nitric acid solution? There we have another strong acid. So 0.25 molar is the hydrogen ion concentration. So pH then is going to be the negative log of that value, which is 0.6, see, 2 significant figures, 60. All right. Number 18. Solution has a pH of 3.16. What's the pOH? Very simple. pOH then would be 14 minus pH. So if our pH is 3.16, let's do this. 14 point whatever we take out here, 3.16, right there. It's 4, no, it's 8, and 3 from 13 is 10. 10.84 is the pOH. Number 20. Which of the following is true for a buffered solution? Well, let's take a look at the answers, so we'll know how to approach the problem. Since it's multiple choice, let's see what the answers say. Solution will not change its pH. Solution resists any change. Any hydrogen ions added will react with. Okay, so it's talking about not just the overall general definition of a buffer, but actually what is the mechanism of what is the chemical reaction that gives rise to the definition. Well, let's say A through D and E. A, B, C, D, and E. All right, is A true? The solution will not change its pH very much, even if a strong base is added. That's true. That's definition, one of the definitions of a buffer. Solution resists any change in its hydrogen ion concentration. That's also true. Any hydrogen ions added will react with a conjugate base of a weak acid already in solution. For 99% of all buffers, that's true. The hydrogen ions, well, actually, that's true for any buffer, whether you make the buffer from a weak acid or a weak base. So in most cases, you're making the buffer from a weak acid, which would be like this, and then it would be in equilibrium with this, plus this, right? If this is weak, this is strong, right? So you add hydrogen ions, reacts with this one, or it increases this value, drives the reaction back, and consumes most of those hydrogen ions. So C is also true. The solution will not change its pH very much, even if a concentrated acid is added. That's also true. If you add a concentrated acid, you're adding hydrogen ion. Well, we just said that. Yeah, any hydrogen ions added. Solution won't change its pH if you add hydrogen ions. That's D is another way of saying C. So E, all are true. All of those statements are true. Right. 24. A solution has hydroxyl ion concentration of 3 times 10 to the minus 7th. The hydrogen ion concentration in this solution is. Okay. In this case, we don't want to calculate pOH because we're actually going to hydrogen ion concentration. So we'll use the equilibrium expression for Kw equals 1 times 10 to the minus 14 equals the hydrogen ion concentration times the hydroxyl ion concentration. Okay? So if the hydroxyl is 3 times 10 to the minus 7, excuse me, wrong place. 3 times 10 to the minus 7 molar. That means the hydrogen ion concentration is this number divided by this number. Okay? So 1 divided by 3 is 0, 0.333. And then times 7 from 14 is 10 to the minus 7. Or 3.33 times 10 to the minus 8 molar. And that's the hydrogen ion concentration. 27. Okay, a weak acid, hypochlorous acid, HOCl, is in solution with dissolved sodium hypochlorite. Okay, so we got this in solution, and we have sodium hypochlorite in solution. All right. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from the HCl to keep the pH from changing? Okay. What we actually have here is an equilibrium between that and this. Sodium is a spectator. So that's the actual equation. And these, of course, are in aqueous solution. So if we add hydrogen ions, we're going to increase this value right here. And it's going to react with that strong conjugate base, because this is a weak acid. and drive the reaction back this direction, consuming most of those hydrogen ions. All right, so the answer there is D. 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? A strong base. Okay, so let's use a real example. Say sodium hydroxide, which has a concentration greater than 1. So sodium hydroxide in aqueous solution, actually that yields all the hydroxides, right? All of those in solution, because that's a spectator. Okay? So this concentration is greater than 1 molar. All right. So if that's the concentration, 1 molar, then we can do 2 different calculations. We can say Kw equals 1 times 10 to the minus 14, which is equal to hydrogen ions times hydroxyl ions. We can substitute this one here, okay, and that becomes our unknown. Right? So hydrogen ions, if this is equal to or greater than 1, what does that do to this one? It's the calculated value, or it's either equal to or greater than 1. This one's going to be less than or equal to whatever value we come up with. So we divide 1 into this. This is 1 times 10 to the minus 14. So this value is either going to be equal to that or less than that. Okay? If we do the pH conversion, then what's the pOH here? pOH would be negative log of 1. So this is going to be 0, right? 10 to what power equals 1? That's 0. So the pH here, this would either be that value or greater than. No, less than, because of that negative, right? So this is either 0 or less than or equal to 0, right? So if it's less than 0, then that subtracts some from this one, and this is either pH 14. pH is equal to or less than or equal to 14. Okay, so let's look at our choices. pH is greater than pOH. Which of the statement is true? Right? pH is greater than pOH. pH is 14. pOH pOH is 0, or maybe a little bit more. So pH is greater than pOH. That is true. A is true. pH is greater than pOH. And remember, the higher the pH, the more basic the solution, which fits with this scenario. If you've got 1 molar hydroxyl, that's definitely basic. Okay, how about the next one? pOH is greater than pH. Well, you can't have it both ways. It's either A or B, right? So B has to be false, right? That's false. Okay, how about C? pH is less than 14? Possibly. Let's see. Oh, if the concentration of hydroxyls is greater than 1, yeah, it has to be this. It has to be less than 14. So this one's true. pH is less than 14. All right. And pH is less than 0. Wait, well, it can't be both. Not with these conditions. pH won't be less than 0, right? Because this is not an acidic solution. If it's less than 0, it's very acidic. And it ain't that. Right? So that one's false. That means E, 2 of the above, is correct. All right. Number 30. Let's see. A solution with a pH of 2 is how many times more acidic at a pH of 6? We're comparing pH 2 versus 6. So if we want to say how many times, we can't use pH because this is a transform. If we want to compare actual concentrations of hydrogen ions, which is what they're saying, more acidic means how many times more acidic is how many times more concentrated is the hydrogen ion, or are the hydrogen ions. So we have to say, we either have to say what is the hydrogen ion concentration for each one, or we have to understand, since this is a logarithm, each pH is a change of 10 times. So if we go this direction, right, it's 10 times to go to 5. To go to 4, it's 10 more times. To go to 3, it's 10 more times. And to go to 2, it's 10 more times. So that's 1, 2, 3, 4. It's 10 times 10 times 10 times 10 is 10 to the 4th power, is 10,000 times more acidic. That's the nature of the logarithmic scale. 10,000 times, which is D. 32. All right. And we get a fresh marker. A buffered solution contains HNO2. HNO2. Okay. HNO2, nitrous acid, is a weak acid. So what would be the conjugate base? Remember, weak acid with its conjugate base, its strong conjugate base, creates a buffer, as long as they're the right concentrations, but we're not going there. So what will be the conjugate base there? NO2 minus. That's it. A buffered solution contains that. Well, how do you get that NO2 in solution? Well, you either titrate this one with a base, or you put this one in solution as the acid. The salt of the base. So if you do that, this yields K plus and NO2 minus. And this is a spectator. That's the one you want right there. Okay? So KNO2 would be the correct answer. That's how you get nitrite ion in solution along with the weak acid. That's how you would mix up your buffer. 33. A buffered solution contains, oh, wait a minute. Sorry, read, 33. Consider the reaction. Acetic acid plus water is hydronium ion plus acetate ion. Which species is the conjugate acid? If we look at that reaction in its entirety, this is the actual reaction that goes on when we put acetic acid in solution, right? So we get, let me put it in the same order. Okay, we're going to put this one here, and then we're going to put the acetate ion. All right. So the question is, which is the conjugate acid? Well, this is the acid. That makes this the base. This would be the conjugate acid. And this would be the conjugate base. There's your answer right there. The hydronium ion is the conjugate acid in this reaction. All right, number 35. Let's see, which of the following is not a conjugate acid-base pair? All right, we did one like this earlier. We're looking for a valid acid and what's left over after one proton is removed. Well, actually, we're looking for one that does not abide by that rule. So if we look at each one of these, we find that the first one has lost 2 protons, right? So that's the false one. The rest of them should be true, right? The next one is acetic acid with the acetate ion. The next one is nitric acid with a nitrate ion. That's true. Next one is dihydrogen phosphate with monohydrogen phosphate. That's true. Lost 1 proton only. And hydrobromic acid to the bromide ion. Yes. B through E, all of those are true. So A has to be our answer. That's the one that doesn't fit. All right, number 37. Let's see, given the following list of Ka values, which of the conjugate bases is the strongest? All right, we have these 4 acids, and we're given the Ka, which, what does the Ka mean? The larger the Ka, the stronger the acid. So if we want the strongest conjugate base, we want the weakest acid. So we want the one with the smallest Ka value. All right. So let's see. A, B, C, let's see. Let's do it like this. A, B, C, D, E. Right, so the first one is cyanide ion. Second one is hypochlorite and NH3 and F minus. And then all. Right, they're not all the same because they're the conjugate acid of these bases have different values. So we want to find the weakest acid to give us the strongest conjugate base. All right. So the first place I would look is the exponent of 10. Right? Minus 10, minus 10, minus 8, minus 4. So the weakest acid there would have 10 to the minus 10. Okay. But we've got two of them with 10 to the minus 10. So we go to the coefficient and compare those. The smallest coefficient there is for ammonium. 5.6 times 10 to the minus 10 would be, would give us the strongest conjugate base. This one right here. Because NH4 plus is the weakest acid. Number 40. Solid calcium hydroxide is dissolved in water until the pH of the solution is 10.39. The hydroxide ion concentration of the solution is, okay. We've worked a problem like this before. We just didn't have to extract the information from the word problem that is kind of convoluted, right? Remember, the first rule of a word problem is to confuse the reader. Because if you don't understand the concepts behind the problem, then it will be confusing. But if you understand the concepts that are applied to the question, then you can extract information from the problem and solve it. Calcium hydroxide is dissolved in water. All right. What is calcium hydroxide, right? Is that right? No. That's a polyatomic ion, and this is a 2 plus charge, so we need 2 of those. Okay? We put that in aqueous solution. What is it going to do? Well, it's going to dissolve and make calcium 2 plus ions. But it's also going to make 2 hydroxyl ions. Okay? So, in order to find out the hydroxyl concentration, we would go, we may not need to even go there. If we know what the pH is, 10.39, then the pOH is equal to what? It's equal to 14 minus 10.39. Right? So that's, let's see, 1 and 3 from 9 is 6, and then 0 is 3. 3.61 is pOH. And the hydroxyl ion concentration then is equal to 10 to the minus 3.61. So we didn't even need to know that to do the calculations. .4. Let's see, 2 significant figures, 2.5 times 10 to the minus 4 molar. Okay? So I was barking up the wrong tree. You would only have to know this if you were given this concentration and you wanted to calculate that. Then you would have to know that this concentration has to be doubled for that concentration. But this problem doesn't address, that's not the right question. The question here doesn't even need to know that. That's fluff, or sometimes we call it blue smoke. 41. All right, choose the pair of concentrations that cannot be in a given aqueous solution. at 25 degrees C. All right. So we're given hydrogen and hydroxyl concentrations. All right. So the first pair, let's do it this way. Like that. Then under each one, we can put it 10 to the minus 13 and 1 molar and 10 molar and 10 to the minus 15 molar and 10 to the minus 3 molar and 10 to the minus 11 molar and then 10 to the minus 7 molar and 10 to the minus 7 molar. All of these can exist. So all right. So how about this one? Well, if we're talking molarity of hydrogen ions and hydroxyl ions, we're looking at this equation. Equals 1 times 10 to the minus 14. All right. So what if we put these in here? If we put 10 to the minus 13 here, and what would be 1 molar? That would be 10 to the 0, wouldn't it? Yeah, anything to the 0 power is 1. So 10 to the 0 is 1 times that. That would be 10 to the minus 13, right? That's wrong, right? It doesn't work. How about this one? This would be 10 to the first power, and this would be 10 to the minus 15 power, right? Minus 15 plus 1 equals 10 to the minus 14. That's good. How about this one? 10 to the minus 3 and 10 to the minus 11. 11 and 3 is 14, 10 to the minus 14. That's good too. This one is a neutral solution. So it's not all. It's only this one is the bad one. Okay? That cannot be at 25 degrees. 42. Let's see. What's the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide in enough water to make 3.2 liters of solution? All right, so what are we given? 96.1 grams. 96.1 grams of sodium hydroxide. Okay, and the final volume is 3.2 liters, right? Right. So if we want to calculate pH, this is going to give us hydroxyls. Once we have the hydroxyl concentration, then we can go to pH. But we don't have the moles yet. We have to convert this to moles. Grams per mole. So sodium is 23. Yeah, sodium's 23. Oxygen is 16. And hydrogen is 1.1. Okay. So that would be 1, 0. That would be 40, 40.01. Okay. So we can find the number of moles of sodium hydroxide, which is 2.4019 moles of sodium hydroxide. All right. How many moles of hydroxide would that be? Exactly the same. 1-to-1 ratio. Oops, not concentration, sorry. That's just hydroxide ions. Okay, now we have the moles of hydroxide, we have the volume. We can calculate the concentration of hydroxyl. Right? Which would be 2.4019 moles per 3.2 liters, which is 0.7506 molar hydroxide. Okay. So if we're going to calculate pH, we might as well go ahead and calculate pOH. That would be the simplest route. So pOH equals the negative log of that value. Take the log and change the sign, which is which is equal to 0.1246 molar. pH equals 14 minus 0.1246. Which is, let's see, start off with, we're limited to 3.2. Yeah, 2 significant figures, 2 decimal places. So we have 13.88 pH. Okay. Let's see. Oh, that's it. Those are the only ones that I picked out. Right. So that will show you the ones that we work today are the types of problems you can expect on the exam. If you know how to work each one of those problems, without from scratch, right, without going to the internet to get your answers, or without using artificial intelligence or asking somebody what the answer is. If you can work these on your own, then you will do very well on the exam. These are the types of problems you can expect. And since we finished the review today, with time to spare, let's see, this Thursday, next Tuesday, which will be what? 21st. Right? Yeah. 21st of April, I won't be in the class. I'll simply Zoom the class from my office, and anyone who has questions can Zoom me at that time. All right. We're done for today.